Okay, so now the topic is post-stack and pre-stack seismic inversion. This is one of the most common approaches that we, or rather most common processing steps that we apply to seismic data for reservoir characterization. So now that you have heard our talks or lectures on a whole bunch of concepts on inverse theory, forward modeling, inversion, and all of that stuff, you should be able to understand this pretty well. So here we need to, whenever you're trying to solve an inverse problem, you have to find out what is your data, what are your model parameters, what is your forward problem, is it a linear or a nonlinear problem, and if it's a nonlinear problem, first of all, then you want to decide whether you want to use a deterministic approach or a stochastic approach. And then if you are using the deterministic approach, you have to choose some optimization method. Okay? So these are sort of different steps, and you have to be quite familiar with these before you actually start to run your inversion. So I'm going to talk about seismic inversion, and this is going to be post-stack and pre-stack, meaning angle stack inversion. And at 4 o'clock, there'll be a talk on full waveform inversion. Okay. So here, the first problem that we identify is that of wavelet estimation. Okay. So when you get some data, whether pre-stack or post-stack, you don't know the source signature, right? So what is the wavelet? And this is essential for running a post-stack or pre-stack inversion. So what is a wavelet? It's basically, there are different definitions. Sharif, in his dictionary, he said that it's a time domain reflection shape from a single positive reflector at normal incidence. Okay. Ideally, this is the source time function that is injected into the ground, but that is rarely measured. So these are some of the practical definitions. So it's a one-dimensional pulse, usually the response from a single reflector. Okay. So how do I estimate the wavelet? There are many approaches that have been proposed here. But before I talk about that, let's say that I have a seismic trace, and let's say that this is my post-stack seismic trace, right? So you can identify 3 inverse problems. One is you want to find the wavelet when the reflection coefficient is known, because this trace has been generated by convolving your wavelet with a reflectivity series, right? And then the second problem is estimation of reflection coefficients or acoustic impedance when the wavelet is known. And the third problem is simultaneous inversion for acoustic impedance and wavelet. Now this is a very ill-posed problem, because if you change the wavelet, you can also change the acoustic impedance and you can match your data. Okay. Though there are some methods for doing this, we really prefer to first estimate the wavelet when we have known reflectivity, and then once we have the wavelet, I apply it on the whole 3-dimensional volume to compute reflectivity or acoustic impedance. So wavelet estimation. So there are many different ways we can do that. So here is a general case of simultaneous inversion of impedance and wavelet. These basically have, if you have a number 10, and this is multiplication of say 2 numbers, A times B, then if somebody asks you what is A and what is B, can you tell them for sure? You can't, right? It could be 5 and 2, it could be 2 and 10, it could be 10 and 1 and all that, 1 and 10, 2 and 10 and 1 and all that combination. So that's a difficult problem. So normally we determine the wavelet from the post-hoc trace or the normal incidence seismic trace using the principles of inverse theory, which we just talked about. One very important thing is that even if the wavelet is known, the estimation of acoustic impedance is not trivial. Okay, and I'll explain to you why. So let's say that this is my seismic trace, which has been generated by convolving reflectivity with the wavelet. Okay? So this is my acoustic impedance profile, and this is my reflection, normal incidence reflection coefficient. Okay? And this is my wavelet. I convolve and I get a seismic trace. And from there, we want to know either this or actually both, right? So why is this problem hard? The reason it's hard is this. If you look in the frequency domain, the reflectivity has all frequencies. Reflectivity is broadband. But wavelet has only a certain set of frequencies. This is band limited. So a convolution is same as multiplication in frequency domain. So if you multiply these two, your seismic trace has missing low and high frequencies because the wavelet has filtered it, right? So if you want to estimate reflectivity to the broadband scale, then it's impossible to do that just from the seismic data. But you can probably put in some prior constraint to be able to do that. So we'll touch upon that a little bit later. But first we look at the wavelet estimation problem. There are many different ways people derive wavelet, but the one that actually works the best is when you have well log. Okay, so here what we do is, let's say that I have a well log. So there I assume there I have two reflectivity, right? Because you measure P velocity, S velocity, so you have the acoustic impedance. So what you do is then try different kinds of wavelets in an optimization problem and find the one that best matches your seismic trace. So here is an example of what has been done here. This is your post-hoc seismic trace, and this is your synthetic data, and this is your acoustic impedance. So I can compute reflectivity from here, reflection coefficient, and my optimization inversion actually gave me a wavelet that looks like this. And how do I measure the quality? I actually compare my traces, synthetic and the observed traces. Okay, so how was this done? Okay, this was done again using an optimization problem. So how do I define my loss function? Here is my loss function. Okay, so this is the difference between observed data and synthetic data. And there is an L1 norm of reflectivity. And also we have L1 norm of the acoustic impedance. So we start with a wavelet and then generate our synthetic trace, convolving it with the well log reflectivity, and then look at the difference, and then we repeat it. And this can be done using, say, gradient descent method. Okay? So pretty clear now? Okay, so these are different weights to the loss function. This is your data loss, this is L2 norm of data, and this is L1 norm of model. And I will show you why that is done. So this is basically to reduce the side lobes, right? And those side lobes are nothing but um, outliers. So if you generate a wavelet here, sometimes you get a whole bunch of small things here, right? And you don't want that. And that can be eliminated using the using that model loss. Okay, L1 norm. Yeah.
Is the L1 norm of what?
I think that's an L1 norm. There's an L1 norm of the amplitudes of the wavelet. Yeah.
It is fine, but when you do it practically, the wavelet which you estimate has a lot of side lobes. So, how do you come up with the best wavelet? I mean, how much should be the side lobes? How much should be the length of the wavelet?
Yeah, so for practical applications, there are lots of problems you run into, like he said. And so the common practice is when you basically derive the wavelet, you should basically restrict yourself within a small time window, okay, near the reservoir, okay? And if you did that, then you will have a lot of these problems eliminated. If you want to use the entire trace to compute the wavelet, it will be bad. Why? Because those of you who are from geophysics know that Earth acts as a filter, right? So as you go deeper and deeper, the lower and higher frequencies are filtered out. So wavelet becomes lower frequencies. So what happens is that what it means is that your wavelet is non-stationary. Okay? That means within different time window, you can have different shape of the wavelet, right? And if you try to fit a one wavelet for the entire trace, you'll run into all those kind of problems. So the best practice is to stick to small reservoir zone or a small window, and there you can assume that the wavelet is stationary, and then you apply this method. Okay?
Compensation in that case, so that's wavelets may go down into
Yeah, if you can apply Q compensation, and if you can do a good job with that, then you can assume that it's a stationary process. But typically, Q compensation is very approximate, and there is a danger of affecting the amplitude, or rather corrupting the amplitudes. And when you do seismic inversion, you are really going after amplitudes, okay? And that can cause some difficulties. And typically, that's one thing for sure. And the other thing is that for reservoir characterization, you are always interested in some time window or some depth window, right? And so it's better to get the wavelet from that window. For full waveform inversion, we have to use a wavelet that works on the whole data set. Okay? What is that? You just run this convolution only within that window. Yeah. Okay. No, you have to do it at the well location. So, but that actually raises one other question. You are deriving the wavelet at the well location. Does it work in the entire volume, right? It may not. So, typically you have more than one well. And if you derive wavelet from multiple wells, you'll see that they're not the same, they're different. So the practical way of doing this is either to use an average wavelet, or going from one wavelet to another, use some kind of weighted averaging. Okay? And wavelet is the most critical parameter in this kind of inversion. Okay? Good. Any other question? Okay. So, for those who don't know much about seismic processing, a partial stack, no, I'll talk about that later on. Oh no. Yeah, so I'll start with inversion of post-stack data, okay? And I'll talk about those figures later on. So how are the post-stack data generated? So here we have a CMP gather, okay? We apply NMO, apply some mute, because at large offsets you have a lot of NMO stretch, and then you stack those and you get a post-stack trace. Now, is this trace good for post-stack inversion? I would expect you to answer after we look at this slide. What is our assumption in terms of estimating the model parameters? What is our forward model of post-stack seismic trace? We have, let's say this is your acoustic impedance, and that's your reflection coefficient. It's positive here and negative there. You convolve with the wavelet, and that gives you data. And what is reflection coefficient? Reflection coefficient, normal incidence reflection coefficient is rho 2 V2 minus rho 1 V1 by rho 2 V2 plus rho 1 V1. Everybody knows that, right? And this assumes that your trace is normal incidence going back and down, right? So our assumption is that the stacking gives us a normal incidence trace, right? You have to be cautious, because if there is an ABO effect in the gather, this amplitude will not represent your normal incidence amplitude. So it's better to use near angle stack, okay? Okay, so now I'm going to talk about how to get to this particular model, right? Our is an inverse problem where you want to go from data to acoustic impedance, right? Again, I like to show this figure, and you know that because of the band limited nature, we cannot actually get to all frequencies. So what is the effect of losing frequencies? The effect of losing frequencies is that if you have a step like acoustic impedance, you have side lobes, and then you also have a shift. Okay, so what we do here is, first of all, this is your data minus synthetics, forward data. So this is your observed data, this is your synthetic data, R is the reflectivity, and there I am putting a constraint on my reflectivity, okay? This is an L2 norm, and that's an L1 norm, okay? So when you do the mixed norm, then optimization, when this was first written, lasso was not that popular. So people were using iteratively reweighted least squares. So what they would do is simply take the Ri square and divide it by the mod of Ri to get to the L1 norm. So we have an L1 norm constraint, and this actually made a big difference. They completely changed the way people were doing inversion. So here is the approach. We start with the starting impedance model, and that is the low frequency model. It's not contained in the data, so you have to supply it, okay? And then we have the wavelet, we convolve, generate synthetic data, and then we repeat in this particular loop. So if you look at the complete workflow, you have seismic data, we have well-logged data, then we have interpreted horizon data. So using these, you generate the low frequency impedance model. So all you do is interpolate in between the well location and extrapolate away from the location guided by the horizons. And all that you do is just filter it typically to less than 10 Hertz, okay? And that's your starting model. And then you run this inversion. So here is an example. This is a synthetic model where I have step-like acoustic impedance, and this is your trace. And we have used a simple conjugate gradient method, and the starting model is the smooth model, and you can see that it actually does more or less good job. And this is your observed data versus synthetic data. And this low frequency information is very, very important. Without that, you cannot get absolute impedance. So now I'm going to talk about real data. And here what we have is this is your post-stack data. It's from a 3D volume. And I'm only showing like every 10th or 100 CDP along a line. So this is the horizon. These are the horizons that was picked. And here is the well location. And using this, I generate a low frequency acoustic impedance model. So you can see this is my detailed well log acoustic impedance. And this is kind of a smooth version of it. And it was guided by the horizon. Okay. And then using this, I run an inversion. And this is my acoustic impedance from the inversion result. So what you notice here is that it actually matches the well impedance quite well. Okay? And then you can see this. These are the sand bodies with low impedance. Okay, so you can see the extent of the sand bodies. These are basically hydrocarbon bearing sands. We're able to see the extent of these. Which curve?
Cursor.
Oh, okay. Yeah, so all that I'm trying to say is that if you look at this blue one here, do you see it now? Yeah, so that is your one sand, that's another sand, this is another sand, and then we found how these sands are, and there's a fault here. Okay? And we did this for the 3D volume. So then other thing we look at is how well we're matching the traces, right? So here we do, this is your data and a few of these traces, your synthetic data, and that's residual. Okay? So we're fitting the data quite well, and we are able to get an acoustic impedance model that is validated at the well location. This complete well information was not used in the inversion. It's the low frequency trend that was used. Okay? So this should give you a very good idea about what are the different steps and how do you QC it, how do you quality control, how do you know the quality, how do you check the quality of your inversion results. The way you do this is first matching in the well location, and then how well are you fitting the seismic traces. Okay? So
induce the high frequency in the seismic?
how do you
bring the high frequency?
So how do you bring the high frequency information? So that is basically, you are getting this everything in the seismic frequency band. So you're not bringing higher frequencies than this. You could do a geostatistical inversion to bring in much higher frequencies that you have in the well log. But in these inversions, the deterministic inversion is only within the seismic band. Okay? Okay? And sometimes we apply some constraint in the model to get step-like structure in there. Okay? Okay. So the next thing we want to look at is inversion of pre-stack data, partial stack. Okay? Nowadays, this is pretty common. So what is a partial stack? I think I had the slides out of order. That's why, yes. I missed some of this. Yeah. So what is partial stack? So what we do is from the pre-stack gather, after applying NMO, we convert those into angle gathers in the angle domain. And for that, you need to know the velocity structure. Okay? So you can then generate traces at different angles. What it means is as follows. So for example, in the CMP, we have traces like this, right? And they're going to different traces. So different angles are going to different traces. So what we do is you gather those up and then make sure that each trace corresponds to one angle. Okay? So now we have a whole bunch of these angle traces. Then to improve on the signal to noise ratio, what we do is we choose some window. So this is your near angle range, this is your mid angle range, this is your far angle range, this is your ultra far angle range. And we stack those. And the reason we don't want to add all the traces because you can then mess up your AVO information, right? And you don't want to do that. You want to improve your signal to noise, but still keep the AVO fidelity. Okay, so once we have the data, then we want to do the forward model, right? In post-stack case, we use the forward modeling approach where you convolved the wavelet with normal incidence reflection coefficient. So here what we do is we use angle-dependent reflection coefficient. And one such angle-dependent reflection coefficient is given by this. So what is the difference? When you set this theta equal to 0, then this term goes away, this term completely goes away, and this term goes away, right? That's your post-stack. And in pre-stack, you have all of these terms. So what is the difference? I really want you to understand that. Tell me, what is the difference in the forward model between the post-stack and pre-stack? Those who are trying to get a job with oil companies, you should be able to learn this and answer this question. Speak up.
Information of yes wave is missing here in most states. Because the specific place, if the incident going on some angle.
Still, I mean, that's not quite the answer. I said, if you throw these terms and throw that term, that's your post-stack, right? However, in pre-stack, you have this. What does that mean?
Angle dependency.
But to that, what are you doing? Why do I want to do angle stacks if I can do this from post-stack case, if I get everything from post-stack? Can we get everything from post-stack? Why don't we have this information?
Regarding the different,
Yes,
different type of equation.
I'm just asking you a very simple question, and I want you to answer. I'm not going to give you the answer. I'm helping you. Once again, I'm telling you that I don't have this term. I have done that. I have that term. I have only this term in the post-stack case, but I have all of these terms in the pre-stack case. What does that mean? Let's say that this is A, next one is B, and this one is C, right?
Let's guess.
Yeah, but what is it?
We applied move out in the answer.
No, that's how we generate the data. So you don't have B and C in pre-stack case, right? What do you have in B and C?
What is density? Then
Good. So you have only acoustic impedance information in post-stack case. In the pre-stack case, you also have shear impedance information and also density information. Density information is here also, but you cannot distinguish between velocity and density because it's acoustic impedance. So why is this important? Why is this shear impedance parameter important? See, this is exactly what Sam was saying, right? We don't have fluid information. The fluid is, to have the fluid information, we have to have information on the shear properties, right? So VPVS ratio or Poisson's ratio is important. And that's why you want to do a pre-stack inversion, okay? Those of you who are appearing at the interview, just take notes because they will ask you this question for sure. Okay? Good. So now I'm going to show you how I do my, okay, now I'm not completely done with explaining this. Okay, so what we do, so what is the forward problem? This is my equation. So given a particular angle, I compute angle dependent reflectivity and I simply convolve it with a wavelet. Okay? For different angles, I have different reflectivity. And for practical purposes, we also use different wavelets. And some people might tell you otherwise, but bottom line is that the reason we do this is because as you do the NMO, right? And NMO causes some stretching, so it's effectively equivalent of changing the wavelets. So for different wavelets, we have angle-dependent wavelet, and I have angle-dependent reflectivity. Otherwise, this is no different from post-stack. What is it? What are the difference between post-stack and pre-stack? In post-stack, you have only one trace per CDP, and the model parameter is acoustic impedance, right? And we use the wavelet and the post-stack reflection coefficient. In pre-stack, we have more than one trace per CDP. You can have 3 or 4 or 5 traces, angle stacks, right? And then we need wavelet for each angle. And we also need to compute angle-dependent reflection coefficients. So it is sort of like running a post-stack inversion or using a whole bunch of traces per CDP. Algorithm-wise, it is about that, okay? And that's why it's very approximate, but that's why this method becomes very, very popular because we know how to do post-stack inversion, and this is just a small extension of this. Okay, so everybody is clear on this? Now, I'm going to ask you, I just discussed this, I hope you remember. What did we do for pre-stack inversion? And for post-stack inversion, what did we do? What are the steps? Come on, guys. Anybody there? Who else is smiling? I know you. What about your other teammates? They're sleeping or what?
They are not playing well today.
They're not here?
Yes, sir, because they are not playing well because we are just playing this.
They didn't come today?
Maybe second half we
Oh. Okay, so anyway, somebody else? What did we do? The post-stack inversion. Come on, you should not forget this. We generated a post-stack trace. We found a wavelet. What else do you need for inversion?
Confusion.
Reflection coefficient.
That will be done by the input. Your input. What do you do?
First we go to the variable style to count the
Still we cannot really.
so first we go to variable set time and then by applying the wavelet they convolve it and find out the ZP.
So that is only at the well location.
Yes sir.
After that, how do you run inversion on the whole volume?
So using the Orton and whole setting working, then interpolate or interpolate.
Very good. So what he is saying is that first you determine the wavelet at the well location, and then you generate the low frequency model. It's very, very important. If you use wrong low frequency model, it will look completely different geology, okay? So you use the low frequency, and the way you generate it is by interpolating between wells and extrapolating away from wells, guided by the horizons, okay? And then you run inversion. So
SGS splitting type of conversion to populate in between.
okay. Now, and it's done more often in geostatistical inversion. Here, mostly they do linear interpolation, guided by horizons. Okay, now I'm asking you, how would you do pre-stack inversion? Now that we have got the steps for post-stack inversion. Of course, wavelet is common, right? But you need more than one wavelet per angle. Okay.
I was having a small question before.
Yeah.
The question is like this: you are speaking about designing a low frequency model. Now, as you said previously, the X behaves as a filter. That means the more the depth, the higher frequencies they do cut off. So under what scenarios or under what context will we choose the dimensions of depth so as to catch up with the low frequency mode?
Okay, so we discussed this, I think, earlier, and I said that in terms of for seismic inversion, we always focus on a small window. Okay, that is your reservoir zone, and within that window, we assume that the filtering effect is constant. So wavelet has already captured that. Okay, and then this low frequency is talking about in the well log data, low frequency in acoustic impedance. Okay, this is low frequency in acoustic impedance or low wave numbers. Okay. Okay, so anybody wants to answer my question? Mm-hmm.
That we have to get the wavelet. Then for each angle is that we have to get the low frequency model, and each angle is that has to be inverted.
Okay. You know most correct. But the low frequency model was for acoustic impedance, right? So you can have 10 angle stacks, but doesn't mean you have 10 low frequency models. You have 3 low frequency models. One is for P impedance, one is for shear impedance, and another is for density. Okay? So you need 3 low frequency models and wavelets as many wavelets as the number of angle stacks. Okay, so I've already discussed these, and then the optimization method is the same. Okay, it's matching all traces simultaneously, and that's why it's called simultaneous inversion sometimes. So here is what the data looks like. This is a field data set. So here you have the partial stack 6 to 16 degrees. So essentially you can take the average of these, maybe 10 degrees. This is a 10 degree trace, this is 20 degree trace, this is probably 30 degree trace, and this is 40 degree trace. Okay? And these are the horizons. Okay? So I need to now get 3 low frequency model. This is your low frequency acoustic impedance. This is the same one that we had used for post-stack case. Then I have low frequency shear impedance. And then I have low frequency density. So then how many parameters am I going to resolve? I'm going to basically get 3 answers, right? For 3 different parameters. So this is your acoustic impedance. And if you look at it, this actually does a little better job than the post-stack. Slightly higher resolution. This is actually pretty good. And then you have the shear impedance. It's not as good as the P impedance, but overall it's not too bad, okay? And then the density. Actually, density does not come out very well from this kind of inversion. You get getting some information, but the resolution in density is not as good as you have in P and shear impedance. And then the next task is to use this information in quantitative interpretation to find out where are the zones that you want to drill. You can make some estimates of fluid content, saturation, and things like that. Okay, and that part I'm not going to talk about. Yeah.
These all the initial models for impedance, density, and shear. They all go for each model, right? Each angle stack. So
No, they're inverting using all the angle stacks at a time. So for the inverting parameters,
so could you repeat the state? One more
so you have, let's say that you have 4 angle stacks. And adding all 4 angle stacks together is estimating impedance, shear impedance, and density.
Okay, so what is the state? First, you make the angle stack.
And you feed all the angle stacks together. You don't do one inversion of one angle stack at a time. See, post stack, it does one phase inversion at one CMP. But in post stack and pre stack case, for each CMP, you need to put this all the angle stacks together for that CMP. And then you issue all 3 parameters at that CMP. Then you go to the next CMP. It's not inverting one angle stack at a time. Okay? So that is why it's called simultaneous inversion. Simultaneously, it was solving for PPVS and density. Yeah, that's pretty much trial and this is pretty much like your own expertise. So typically we do 5 trace stack. So that keeps the signal to noise ratio at a higher level and does not basically destroy your amplitude. But here we use 10 angles because this is much better signal to noise ratio compared to other data that we have seen. Okay.
PPVS and density, all 3 of them, that's what you mean.
In post-stack you get only acoustic impedance. And pre-stack you get acoustic impedance, shear impedance, and maybe density. So from there you derive VPVS. Okay? Okay? Assumption here is that your earth is layer cake at each CDP. But in reality, it's not. So there are a lot of assumptions made in here, built in here. So if the subsurface is really strongly laterally heterogeneous, then this is going to fail miserably. So that's why you have to do full waveform inversion and in the elastic medium. That is coming up only now, but doing full elastic waveform inversion is computationally very intensive. Okay, so that's all I had, and what I did is I forwarded my slides as well as the 2 exercises to Somin, who's already sent him to you. So there's one on local optimization that we will practice here in the afternoon also. And I gave another one that I promised I would give you. That was the linear Bayesian inversion. And those of you who are interested, please work on that as well. and we go from there. Okay? Yeah, please.
Yes, density, and now if we want a porosity distribution in the entire reservoir, what will we do with that?
Yeah, so how do you measure the porosity? So generally, there are multiple ways, and the easiest way is to basically at the well location we cross plot impedance against porosity, and then that basically can then be used. The same equation can then be used to convert impedances to porosity everywhere. Okay, and then from the VP/VS ratio we try to talk about saturation and other things.
Actually, we are resisted into time domain in this equation. So, sir, in some area, optimization is making more effective as compared to time domain migration. So, sir, what about what our thinking about the depth domain?
Yeah, some people are doing development inversion, but in also conversion, a lot of things have changed. So one can try that, but it's not that straightforward.
I have tried, but the website is not stationary.
Yeah, because what happens is that, the thing is that what's the way I think they're doing? And it's going to be non-stationary because there are different sections in the different. And convolution model is not very essentially. But people have tried this, but not very successfully. That's why we have just moved into some other approaches. So roughly you can just look at the AVO in depth domain and that's it. Okay, so it's lunch break now, and we'll meet at 2 o'clock or 3 o'clock, right? At 3 o'clock, and then do some exercises and go from there. Okay?